Hello everyone, welcome to this session. So in this session we will solve one numerical problem on bending stresses using flexural formula. In the earlier video lecture we have gone through the symmetrical unsymmetrical I section as well as the T section beam, and we found the bending stresses develop into that cross section of the beam by using the flexural formula. So in this session we will take one more problem which is of a different section of the beam. So already we are using the sections of the beam for different sections. So here one more section is there. So on that section we will take one problem so that you can clear the things. So I will read the problem first. Maximum bending moment of simply supported beam is 10 kilonewton meter. The cross section of the beam is as shown in figure. Find the maximum bending stress in tension and compression side. So this is the problem, and the cross section of the beam is in front of you. So there is a bottom central square hole is there. The dimensions are there of the central hole as well as the total section. And in the problem, there is a maximum bending moment is given of a simply supported beam, which is 10 kilonewton meter magnitude, and the cross section is there. And also they ask to find the maximum bending stress in tension side and the compression side. Means bending stress it is showing by the symbol sigma, and in the tension sigma t, and bending stress in compression sigma c. So that two values we have to finding out here. Okay, so let us solve this problem. First of all, we know that position of the neutral axis. Whenever your first step is there of any section, first of all locate the neutral axis, that is the position of the neutral axis, and that can be located by y bar, either from the bottom face or from the top face. So here y bar, the formula is a1 y1 minus a2 y2 divided by a1 minus a2. Why this minus is sign is taken? Because a1 is the total area of that section, and a2 we have minus because the small hole is there. You can see here, this is the total section of the beam. It is a rectangular shape and there is a small hole is there. So you have to minus this small hole from the total section, so that we'll get the moment of so that we'll get that actual location of the neutral axis. So let us this a1 y1 minus a2 y2 divided by a1 minus a2. So first of all a1 is the area of cross section of this rectangular section of the beam. So 120, you can see 120 and 60 what 120 is the height and 60 is the breadth of this section. So we'll get the area 17200 mm square. And y1, that is the centroidal axis distance of the centroidal axis, that is a 120 is the total distance divided by 2, which is 60 mm. And a2 is the area of that square hole. So this square hole is there at the bottom, whose dimension is 20 by 20, and we'll get the area 20 into 20, 400 mm square. And y2, how to determine the y2? That centroidal of that square hole, 20 plus half of the 20. So 20 plus half of the 20 means, suppose we are finding the distance from the bottom face is this of this section, so it is 20 plus half of, and also the height of the square hole is 20. So you have to come at the centroidal axis of this square hole, so 20 plus half of the 20. So that's why 20 divided by 2 plus 20, so value is 30 mm. Getting? So then you put all the values a1 y1 a2 y2 in this formula of y bar. We'll get the, so by mistake here 72,000, it is not 72,000, it is a 7200 only. So please make a correction here and do the calculation for y bar. So we'll get the, after calculation, the yt value 61.76. Here it is not a 72,000, so value is a1 7200. Okay, so just make a correction here only. So after calculation we'll get the yt 61.76 mm from the bottom face. So that yt is the that neutral axis position from the bottom face, that is 61.76 mm. Therefore distance of CG from the upper extreme fiber, so this is from the bottom of the CG, if you want to finding out the from the upper extreme fiber, so you can subtract this YT from the total height. So total height of the section is 120. If you subtract this YT value, so we'll get the YC. So YC is the CG from the upper extreme fiber. So that value is 58.24 mm. Getting this YT and YC, make it clear this Y bar, because we are measuring all the distances Y1 from the bottom face. That's why this YT, and our below the neutral axis there is a tensile stresses are developed, or tension zone is there. That's why this YT is there. And upper of the neutral axis there is a YC. So if you subtract this YT from the total height, we'll get this YC. After that, moment of inertia of the section about an axis passing through its CG and parallel to the XX axis. So moment of inertia about an axis passing through its CG. So that moment of inertia of whole section we can find by using the formula Ixx1 minus Ixx2. Why it is minus is taken? Because there is a square hole is there. So we have to minus this moment of inertia of this square hole. Then and then we'll get the moment of inertia of this remaining section. So for that formula is I is equal to Ig1. So G1 is the we can say the total rectangular section, and G2 is mentioned for the square hole, small square hole dimensions. So moment of inertia of small square hole. So first of all, Ig1 plus A1 H1 square minus Ig2 plus A2 H2 square. So first of all, Ig1 means moment of inertia of total rectangular section, this exterior rectangular section, that is a BD cube by 12, that is a B is 60, D is 120 is cube divided by 12. After that, A1 of this section is 7200, and H, how to determine the H? It is a CG, distance of CG from the neutral axis. CG of this section is 60, because CG, centroidal axis, is half of the 120 of this section, and our neutral axis position is 61.76. If you take the difference, so we will get the H value from the neutral axis distance of the CG. So this H1 is determined. So you just remember this, how that H1 and H2s are determined for the each section. So we are determining for the larger exterior rectangular section of this beam. So that's why it is a Ixx1 total formula. After that, minus Ixx2. So now you concentrate on to this small square hole. So for that, the moment of inertia is BD cube, means dimensions are 20 by 20. So 20 into 20 cube divided by 12, plus area of that square hole is 400, and the distance from the neutral axis of that CG of this square hole is 61.76, and the CG is this 20 plus half of the 20, that is a 10. So 10 plus 20 is 30. So if you take the difference between that neutral axis and the CG of this square hole, we'll get the H2 value. After doing the calculation of hole, we'll get the value 8.60 into 10 raised to 6 mm raised to 4. So that is nothing but the moment of inertia of whole section, excluding the square hole. After that, by using the flexural formula, we know the flexural formula, that m upon I is equal to sigma upon y. M is the maximum bending moment or moment of resistance, I is the moment of inertia of whole section, sigma is the bending stress, y is the distance of the neutral axis from the extreme fiber, right? So if you want to determine the sigma c, why it is sigma c is taken? Because bending stress induced into the compression side, and your upper part of the neutral axis is compression side, and below the neutral axis is tension side. So we know here it is only m upon I into y. So y means here it is yc is taken. So neutral axis, distance of neutral axis from the top fiber. So that distance is 58.24. So we have determined earlier this yc. You can see yc 58.24. So if you put that yc value in this formula, maximum bending moment is known 10 into 10 raised to 6. I is we determine 8.16 into 10 raised to 6, and yc is 58.24. So now sigma C value is coming 67.72. After doing the calculation on calculator, the value is coming 67.72 MPa. MPa is the megapascal. Instead of MPa, you can write Newton per mm square also. So Newton per mm square and MPa is one and same. MPa is megapascal. So this is a bending stress induced into the compression side. That's why sigma C. The notation is sigma C because bending stress in compression. After that, bending stress in tension side. So that symbol is sigma T. T is tension, C is compression. Again, the formula is same. Flexural formula m upon I into yt. There is a change is there only for yt. So yt is the distance of neutral axis from the bottom fiber, because in the bottom side our tension zone is there, or tensile stresses are there below the neutral axis. So that's yt. You just see that here it is yt is determined. Yt is the distance of the neutral axis from the bottom fiber, 61.76 mm from the bottom face or bottom fiber. So put that yt value here. M is known, I is also determined, and yt is also determined. If you put all these values here, so we'll get the value of sigma C. So that sigma C value now 71.81 MPa or megapascal. So sigma C is nothing but the bending stresses in develop in compression side or compression zone. So sorry, here it is not a sigma C, it is a sigma T. Actually this sigma T value is there, so we just make it correction here. Sigma C, it is not a sigma C, it is a sigma T. Okay, so sigma C is 67.72 MPa, and here it is, make it correction, you just write here T, it is a sigma T is equal to 71.81 MPa. Right, I hope you understood this problem of a different section. Actually the rectangular section is there, but there is a bottom side square hole is there, that's why. But remaining procedure and the flexural formula to determine the bending stresses in compression side as well as in the tension side, that we can use as it is, which is used in the previous problem. Okay, so in this way you can determine the bending stresses in the beam. Thank you very much.